So if not, we are just in time to start the first lecture. So the first lecture will be from Laura Covi. She is professor at Goettingen University. She's an expert in all aspects, actually, of dark matter, theory and phenomenology, and astroparticle physics in more generally. So Laura, I think that if you want, you can start. And to the students, remember, put down your notes, and at about halftime, we can leave some time to you to ask questions. So enjoy.
Okay, wonderful. So I will try sharing now my tablet. And I have just to say that if I have the tablet on, I don't really see the chat, and I don't see much of the rest of what's going on Zoom. So yes, so it would be good if you could collect the question, and then in case we can discuss them at the break or in the middle, because as I said, well, if you ask me, of course, by voice, I can react even earlier, but otherwise, even if you write the question in the chat, I will not be able to see it. Okay, so just another comment. Of course, usually lectures online are not really so incredibly inducive to discussion, but I will try to keep some time in the middle and at the end so that we can have a little bit of exchange. And of course, we have also the office hours and the exercise classes, where I hope there will be also the chance to have a little bit more interactive kind of lectures or discussion. So yeah, so I hope I will not just talk to myself, and then that you will stop me if I also go too far or too fast. Okay, so this lecture is, the subject of course is dark matter, and actually particle dark matter. And I decided to start this first lecture with a little bit of introduction. So I can give you a little bit the schedule or the plan of the lecture. So plan. So this first lecture will be an introduction both on dark matter and also on cosmology a bit, since I am the first lecturer in this series, and probably you will get some more repetition about these also next week, but for this week I will introduce what I need. So this will be introduction to dark matter and cosmology. Then I will have two lectures. So the lecture 2 and 3 will be mostly on the weakly interactive massive particles, so the WIMP mechanism and the phenomenology of the WIMP. And then the 4th and the 5th lecture will be about other candidates. In particular, I will probably start with the axion and ALPS as dark matter. But I will probably also touch WIMPs and other non-equilibrium candidates. And you will, I mean, here there are lots of acronyms, but we will see later on what they really mean, and I will try to explain it in the lectures. Okay, so this is a little bit the plan, and today we'll start with this introduction to dark matter and the cosmology. Okay. So the first, then it's a bit, I decided to start a little bit with the history of dark matter. Now, if you are interested in the details, you can see there is a very nice review by Bertone and Hooper. So you can, here I will give you the number, 1605, the archive number. 04909, where you see a little bit the history reviewed. And the history of dark matter is actually quite old. And in that sense, we are nowadays in the 2020, and it's approximately 1 century ago where first this concept of dark matter arose in astrophysics. So the first evidence was actually coming from the Milky Way. So the first evidence from excess velocities in the Milky Way. So stars in the Milky Way seem to be too fast. And the names associated with that are actually name of Kapteyn, Oort, Jeans, and Lindblad. So they were mostly astrophysicists. And they were finding a discrepancy of a factor about 2 with respect to what was expected from the density, of course, of stars. And so it was not a big discrepancy, but it already at that time, there was some evidence that the visible matter was not everything. And so this concept of dark matter already arose. So I write here, it's a factor of 2 discrepancy. And the names, as I said, are Kapteyn, Oort, Jeans, and co. And so at that time, it was mostly looking at very near the neighborhood, of course, of the Earth. So that was exactly looking at the Milky Way. But the next piece of evidence came instead from a little bit further away, and that was actually in 1933. So that is the famous paper by Fritz Zwicky. And he had a paper on the Coma cluster, where he was actually mostly interested on the cosmological aspects, in particular also the expansion of the universe, etc. But has at the end a section about the motion, again, in this case, of galaxies in the Coma clusters. Sorry, not, that's wrong. Let me erase. Draw. Let me see. Okay, now I can't draw anymore. Let me see. Yeah. And this is, in some sense, is one of the most detailed, if you want, one of the first very detailed paper trying to argue about the existence of an additional component. And the argument is, of course, as usual, we use it even today. So if you want, this is the basics evidence was using the virial theorem. So the fact that the kinetic energy, the average of the kinetic energy has to be equal to minus the average of the potential energy. Of course, a minus sign because the potential energy is negative since it is a bounded system. And from this relation here, one can argue again about the velocity that the objects in a cluster have to be. And of course, in this case, this average was a time average. And what it was found, of course, if you want gain the usual expression for the kinetic energy, and you assume that the velocity is practically circular, then you have the famous, here you have, neglecting here the mass, of course, because you can cancel from the 2 parts, you get exactly the relation 3/5, the Newton constant, the mass of the cluster within a particular radius divided by the radius. And this means also that from these you can get the velocity squared, and of course also the dispersion. The dispersion of the galaxies was again 1/3 of the velocity squared. And this one then was again, you see it is the expression before, so it was again a quantity proportional to the mass of the cluster divided by the radius. And in this case, this dispersion velocity that Zwicky measured was about 1,000 kilometers per second. And this was a factor of 400, more or less, of discrepancy with respect to the expected, if you want, dispersion relation, which would have been dispersion velocity of, a factor of 500 less. So in that sense, this is a very strong discrepancy, not just a factor of 2, like the discrepancy you had for the case of the Milky Way. Now you can read the paper, it's very clear and it's actually quite instructive. The only point is the paper is in German, actually original. Zwicky, being Swiss, was actually writing papers also in German. I think you can find also on the web a translation, and it's quite instructive because it's a very simple argument and it's a very clear expression and a clear result. It's also true that one has to say that Zwicky at that time was using only 6 galaxies within the Coma cluster, so the statistics, of course, was not incredibly large. Now, nowadays, of course, we can do better. So from the clusters, we have even better evidence from the gas in the cluster. So I just mentioned it here. So nowadays, more precise measurements based on the gas. And we know nowadays that the gas is actually a main part of the matter in the cluster. I mean, the baryonic matter, of course. And you can again estimate what is the relation between the temperature, if you want, of the gas and the potential energy that is again in the gas. And for this, you need a little bit of hydrodynamics. So I can just write here very quickly the basic formulas. So if you assume hydrostatic equilibrium and always also spherical symmetry, so in that case, we have that the pressure would just change according to the distance from the center. And it would be something which is constant, which depends on the radius. So not a constant, but some function of the radius times the density. And moreover, one has for an ideal gas that, of course, the pressure, you have the famous formula PV is equal nRT in thermodynamics, which means that the pressure is proportional to the density times the temperature. And so if you rewrite this expression, taking into account this one, you find the following relation. You can take the derivative here in the you have a P over R, the logarithm of P in the logarithm of R. And this one you can rewrite as an expression of the logarithm of rho in the logarithm of R plus the temperature part. And then, of course, you can then rewrite those as, unfortunately now I will lose what I write, but okay, I have it in my notes. You can rewrite this expression as a minus R over P. Sorry, we can reinvert this expression. Sorry, of course. Let me rewrite. Yeah. So we get practically inverting this expression. We get this d logarithm of rho in the logarithm of R plus the same for the temperature. This is equal to the inverse of the, so minus R over P in this case. And then I have a rho times A of R, which is the expression we had before for the dp in the air. And here again, the raw part you can actually rewrite very clearly using in some sense, the expressions of the pressure here. You can cancel it out. So you remember the pressure is rho times T. So here you get a minus air over temperature. Here you get a constant, which is related to the mass of the gas practically, divided by the Boltzmann constant, and then this A of R. This is, of course, this mu parameter takes into account that the gas is not only hydrogen, so it's not only MP, it can contain also other types of molecules, and that's in some sense, it's a kind of average mass of the gas as a function of the proton mass. And now, of course, this is a relation that you cannot solve so directly, but you can see that from empirical observation, you see that the temperature is actually constant for a wide range of radii. And the density is usually going decreasing like 1 over r squared or 1 over r to the minus 1.5. And this gives you practically an estimate and a relation for this A of R, which is at the end of the order of, so it's again, of course, again connected to the mass of the cluster divided R square. And if you then put this into this relation, you get actually a relation for KT. So as I said, the d logarithm of t over the r is practically 0, and this one here is something which is constant because the logarithm is just the exponent. If the density goes like r to the minus 2, then you see that KT is actually just related directly to this GNR 1 over R. And these then gives you something like 1.5 or so kV times the mass of the cluster divided 10 to the 14 solar masses, and 1 over the radius. So here I have also a 1 megaparsec divided the radius. And again, from this measurement, you can again estimate that the temperature that we can measure from the, of course, from spectroscopy of the light coming from the gas, we find that this temperature is approximately of order 10 kV and not 1.5. So in that sense here again, you find that if you compare it with the measurement, you find actually a factor 5. So hotter if you want. Okay, so we see that the factor 400 that Zwicky was obtaining in the old days was actually a bit overestimated, but still there is quite a discrepancy. And the main point, of course, in the measurement of Zwicky was that he was not considering the gas, he was actually considering mostly the stars. So he was summing up the mass of the stars to make an estimate of the mass of the cluster. And instead, we know that nowadays that most of the matter, the baryonic matter in the clusters are actually in the gas. Okay, so this one is again nowadays a better measurement and one of the evidences we have about the dark matter. But now let me come to the last piece in some sense of evidence, which actually came out much later in the 1970s. So here we have a jump in some sense from the 30s to the 70s. And this is connected to the rotational curves of galaxies. Sorry, today apparently I have a problem writing galaxies. And this, of course, this piece of evidence is connected to Vera Rubin and her group, who was doing measurement, astronomical measurement of galaxies around the Milky Way. And of course, what they did find out is that these curves are flat. And this is the usual picture, which I can also show you later on. I have also a few slides I can show you later. But the evidence, just as a sketch, of course, was that what they found is that depending on the radius away from the center, they were finding actually data points which were more or less aligned and along a constant velocity. So here we have a velocity and in kilometers per second, for example. And here we have the radius in kiloparsecs. And what usually is this value, of course, of the plateau depends on the galaxy. It's usually around 50 or 100 kilometers per second. So I can write here just as indication something like 100. And what I found out is that this was going out for relatively large radii up to 30 kiloparsec or something like that. While the baryons are usually concentrated in the real central part here. So in some sense, you could expect something like this from the disk. So the disk was actually having a maximum at around 10 megaparsec or so, kiloparsec or so. And instead, the real curve was doing something like this, okay? So the problem was here, therefore, that the density seemed to continue to be present also at large radii, where the luminous matter was evidently not there. And that is exactly the discrepancy. So luminous matter only small r. And if you do the simple expression also here, looking only at radial velocities, you have again the usual expression that the kinetic energy along the radial direction has to be equal to the centrifugal force, if you want. So you have, as usual, something like mv square over r is equal to gn m, the mass within the radius r, divided r square. And here, of course, again, you can cancel the mass, you can cancel one radius. You see that in order to have a v square constant, here you need a mass which grows like the radius. And then, of course, you drop these dependence. Otherwise, if the mass becomes constant beyond a particular maximal radius, then you would expect the velocity to go down like 1 over r. And this is exactly the behavior here, which I call here disk. And this one is the one often called halo, which means you need a density of dark matter which goes on wider, much further away than the luminous matter does. And it's usually giving you, in some sense, so a density and also a galaxy which is much larger than the visible galaxy. So in that sense, you see here very clearly that you need, as I said, m of r growing like r. And this we can immediately also see what that means. So of course, the mass within the radius r is, in the case of a spherical symmetric object, is 4 pi, the integral from 0 to r in dr prime. And of course, here we have the density, and here I write dark matter as a function of rho prime. And then, of course, we have the r prime squared. So we see immediately this one should grow like r in order to have the behavior of the velocity that we observe. And here you see immediately that it's clear that in order to get something here which grows like r, here you need the integral of dr alone. So in some sense, you need rho dark matter to be proportional, going like 1 over r squared. Let me use rho 0 like r squared. And then, of course, if you have, let's use here also r prime. Now, of course, this r prime square is just an approximate result. We do not really need the velocity to be exactly 1 over r squared. Also, we see that in this case, if it is really 1 over r squared, we have a little bit of a problem at the origin, in the sense that there you could have an infinite density. So in that sense, this is one of the problem, and you will see later on also one exercise to trying to see exactly what shape the dark matter would have. Nowadays, we have, in some sense, also numerical simulation trying to tell us how this dark matter profile really goes. And usually the kind of profile that we have is something which has also a r to the gamma, and then some constant. Here sometimes squared, sometimes with some other exponent. So the shape that nowadays is used is of this kind, with different exponents, alpha, beta, and gamma constant exponents. And we will see later on, this is actually quite important, in particular for detecting dark matter in the case of a weakly interacting massive particle, because of course, in that case, you could have annihilation of dark matter wherever the density is sufficiently large. And therefore, the fact exactly how the dark matter density grows in the center, it's of course quite an important information, because this will give you a stronger or weaker signal in the annihilation of dark matter. And this we will discuss when we discuss more in detail the phenomenology of dark matter. Now, these profiles have different names. This we will also look at it more in detail later on. But of course, one you probably all know is what is called the Navarro-Franken-White profile, which has, in this case, 2, 1, and 1 as here as factors. But you can also have other profiles with different exponents. So in that sense, and one of also which is used more recently, even more often, is also the Inasto profile, where instead of being really a power law, the growth is actually a logarithm of the radius. So in that sense, this is indeed one of the possible, also still possible profiles. And in some sense, yes, so just to go back to the previous slide, in order to have this behavior, you see this behavior is true at large radii. So we know that this has to be like 1 over r squared at those radii. But of course, this doesn't give us really very much information about what happens in the center, and also what happens at the outer skirts. Because of course, at a certain point, the galaxy has to finish. And in that sense, the density has to go down faster than 1 over r squared in order, in some sense, to end the galaxy. So this means this behavior here is just behavior in the intermediate range. And of course, if you want, for example, in this case, you see that for outer radii, this goes like a higher power here. So you have gamma plus beta alpha, and therefore you could also have a stop if you want, or a end for the galaxy. And moreover, as I said, the real behavior of the dark matter in the center of the galaxy is still quite unknown. And this is one of the main issues when you want to look for dark matter, for example, from annihilation. Okay, so this one was more or less all I wanted to tell you about the evidence. Of course, this is all evidence based on gravitational interaction. So yes, so let me erase again. Is based on gravitational interaction. And it is also, and it is present at different scales. So if you want at different length scales, so we see that some evidence comes from the clusters, which are very big objects. Other evidence comes from the galaxies, which are smaller objects. And it should be clear that we have also other evidence, which I will get to in a minute, which is instead connected to cosmology. So that is connected in some sense to the universe as a whole, to the maximal length scale we can really consider. And this I will discuss in a minute after I go a little bit through the to the cosmological introduction, if you want. But important is if you want to interpret, of course, these evidence for if you want to interpret it as a particle. So if dark matter, if you want, is a particle, then it's clear that the hope would be that it should have also some other interaction than gravity. And since we know that practically all particles we know of in the standard model do not have only the gravitational interaction. But of course, in principle, it could also be that it's just purely, yes, so other interaction than gravity. And here, the other comment I want to make is that, of course, these evidences we have seen so far, it's in principle, of course, there is a possibility to fit it, if you want, also doing a different thing, not adding additional component of matter, but modifying gravity. And in that sense, this astrophysical evidence is not really telling us if the particle, it has to be a particle or an additional component, or it has to be a modification to GR. Inside the evidence I will discuss later on, which is connected instead to the structure formation. There, in some sense, we have a little bit more a feeling, or at least it works quite better by using an additional component of matter and using the normal standard gravity, because in that case, the evidence we have is really connected more to the evolution of the universe and the growth of structure. And I will get to that in a second. Okay, so this one where if you want local evidences, and of course, I mean, the one evidence is that dark matter is there. And the other evidence, if you want, is also, that I didn't mention it, is that dark matter has to be either stable or incredibly long-lived. So it is still present in our galaxy, and it is still present in clusters. So in that sense, we need some particle which has a lifetime long enough, if possible, even a stable particle. And to that, we will go back tomorrow when we discuss, of course, the WIMP mechanism. Okay, so let me go now to the global evidence. So the evidence connected instead to the evolution of the universe. And this leads me to the introduction to cosmology and the global evidence. Okay, so probably most of you have already followed a course in cosmology, but nevertheless, I want to give you a little very short introduction. So one of the basic principles of cosmology is the cosmological principle, which tell us that the universe is homogeneous and isotropic on a large scale. So this is actually nowadays also supported by evidences. We know that if we go backward in time, or if you want further away from us, any deviation from an homogeneity and isotropy is actually suppressed and becomes smaller. So of course, locally, we have a highly non-homogeneous universe. Indeed, in the solar system or also the Milky Way, we see stars or planets, etc. So the density, for example, is surely not constant or nearly constant. But on the other hand, if you go backward, as I said, in time or further away, we see that we go towards this homogeneity and isotropy. And it's clear that only in that case, if you have exactly these assumptions, you can really describe the universe through a simplification, so which is given by the Friedman Robinson-Walker metric. Sometimes people add also Lemaitre, depending where you are from. Well, I can put also Lemaitre. This metric is exactly the metric which has these homogeneity and isotropy characteristics. So we can write just the line element to be, I have a dt square minus a square t, a scale factor here, which is a function only of time. And then I have a dr square plus, well, actually here in principle, I can have something more. So let me write the full expression. Of course, I mean, at the end, I will look only at the flat case, but here in principle, you could have also a non-flat case. And this in practice is exactly the metric we will use later on to get practically the here I think it's a square, to get the Christoffel symbols in principle and the Riemann tensor in order to plug it into the Einstein's equation and get really the evolution of the universe. Now, you see immediately this metric is not a Minkowski metric, of course. You have here the scale factor, which it will, in that case, not, it's practically 1 for the Minkowski metric. And you have also this K factor, which is connected to the spatial curvature of spacetime. So depending on the value of K actually, you can always rescale the radius so that the K, you can choose to have value plus or minus 1 or 0. And of course, K equal to 0 correspond to the flat spatial universe. K equal to 1 is the closed universe. So the case where you have if you want something with closes like a sphere, and you have the K equal to -1, which is negative curvature, and this would mean an hyperbolic space. So this one would, if you want to have the geometry of an hyperbole as a spatial geometry. And nowadays, of course, we have a result from the CMB, which if I have time, I will show later on. And we know that K is probably very near to 0. So that's why in the expressions I will use later, I would often put actually directly K equal to 0, but not always. Of course, in some cases, you can also do every computation with K different from 0. So this is not the problem. And if you want to know why, of course, we can assume that K equal to 0, apart from the data, is also for the assumption that we had an inflationary phase. And I guess this will be discussed probably next week by Chris, the fact that you actually flatten the universe during inflation, and therefore probably this is one of explanation why now the curvature, the spatial curvature of the universe is very small. Note also that when I talk about curvature here, I think I talk about the spatial curvature and not the space-time curvature. Of course, the fact that you have a scale factor here depending on time, it means that there is a space-time curvature. So the space-time is not flat, but the space can be flat. And here I want just to add one thing which can be useful and maybe we will use also later on. And this is to add the conformal time. Conformal time is denoted usually by different letters. Some people use a tau. I use an eta because I use tau for other things. So d eta is, you define it as dt over the scale factor. And so if you want, you see that therefore, if you rewrite the line element as a function of this conformal time, you can rewrite it in a easier, if you want, form. So we have a scale factor in front, and then we have the eta squared minus the usual, if you want, yeah, the r squared, what, minus k r squared minus r squared, the omega. So you see that in this case, you can see that the metric is practically conformal to the Minkowski metric. Especially if you have k equal to 1, of course. Sorry, k equal to 0. So in that case, you see that if you choose k equal to 0, which is, as I said, quite a good assumption, then you see that here what you have is that you have just rescaling, if you want, your Minkowski metric, depending on the conformal time. And this means it has the advantage that therefore the light rays just travel with ds square equal to 0. So they travel as in Minkowski, but in conformal time. And this is useful for many things when you want to see how a light ray moves. So for example, radially, you see that d eta is equal to plus or minus dr and the square root, if you want to keep the curvature, but usually we don't, okay? So in that sense, if you want to look at a light ray traveling in this geometry, you just look at the conformal time and you have practically a very simple expression. You can use in some sense everything you know from Minkowski. Okay, but this is just a starting point. Of course, what we want is the evolution equation. I see that I am more or less at the middle of the lecture, so maybe I can already stop for questions, because otherwise, if I start with evolution, it will take me some time to get to the expressions. So are there any questions so far?
Yeah, any question from the students? You can just, yeah, Konstantinos.
I can't hear you. Should I look in the chat?
I don't see questions in the chat. Konstantinos Kritos, are you trying to ask a question? We don't hear you. Can you write the question in the chat?
Can you hear me now?
Yes. Please switch the camera.
Yes.
So we can see you.
Yes. Hello.
Hi.
Hi.
So the question is, in the virial theorem, you wrote a factor of 3/5.
Yes.
So where is that factor coming from?
Wow. Okay, I don't. Well, I would have to chase it out. I don't remember exactly. I have these notes from some time ago. So yeah, so I guess this is the usual potential, and you have, of course, to consider here the average of the gravitational energy. So in that sense, it is Gn m over r if you want the potential, but you have to take this time average. So there, I would have to look it up. I can try to give you the answer tomorrow, perhaps during the discussion.
Okay, sure. And there's another question. So when you showed us the rotation curves,
yes,
you said that we expect the curve to drop at larger radii. The question is, do we have evidence for that the halo should end somewhere, or is it a speculation?
well, we don't have evidence of the ending it somewhere. In some sense, the problem is, of course, that we don't have luminous objects very far away from the center, so that we can really see the dropping down. So in most of the objects, we just see the plateau, and we don't see then a dropping. So we don't know exactly where the halo finishes in that sense. Okay. But we know that at the end, the bounded object is finite. So we know there are, of course, galaxies near to other galaxies. For example, in our case, we have the Milky Way, and there are a couple of other M31, other galaxies nearby. So we know that there must be a kind of, there are two different objects. So there must be an end in some sense of the galaxies. And usually, as I said, you assume that there is a cutoff at a certain point, or in any case that the density drops. And in the expression I give you here, it's clear that, for example, if you have here a gamma equal to 1, and here beta equal to 1, alpha equal to 2, you have a drop of 1 over r cubed. 1 over r cubed, of course, would give you here, if you look at this expression, dr over r. So the matter here, m of r, would go down, like it would just grow like a logarithm, which is going pretty slow, but it's still in some sense growing with the radius. What usually people do is to put a maximal radius here. And since the dependence on this maxima radius is logarithmic, it doesn't really matter very much what radius you put there. Okay, so it's not you're not very sensitive at what is the size exactly of the galaxy.
Right,
And
I see.
as we will see then also on Wednesday in the lecture when we look at the phenomenology of the WIMP, most of the signal you want to have is actually coming more from the center of the galaxy. So you are more interested what is the density in the center than what really happens in the outskirts in some sense.
Thank you.
Yeah. There is another question I see. So can you ask directly?
Yes, I have a question. Can you hear me well?
Yes, I can hear you.
Yeah. When you talk about dark matter, you said that if dark matter is a particle, then it has the possibility to have other interactions. I'm asking, is there any other possibility that dark matter is not a particle?
Well, as I said, in principle, of course, in these equations, you see that you're always balancing some kinetic energy with the gravitational potential. So, of course, if you change the gravitational potential, you could also live without dark matter in that sense. So, but it's not completely true. We'll get back to this point later on. But at least from the rotational curves of the galaxy, you could fit them without dark matter, changing the law of gravity. In particular, this goes under this name of MOND, Modified Newtonian Dynamics. And for the rotational curves of galaxies, what you have to do is to have practically minimal acceleration if you want. So you have to change the force of gravity, but only when the acceleration becomes very weak, which because it's outside, if you want, the center of the galaxy. Now, the problem is a little bit that if you start to fiddle with the gravity, it becomes quite difficult to really write a fully relativistic theory. So for MOND, there is a formulation which tries to put all these in a footing which is equivalent to general relativity. But for doing that, you have to extend general relativity to be a theory with a scalar, vector, and if you want, instead of just a tensor, if you want degrees of freedom, also a scalar and a vector. So this is goes also under the name of TeVS, so tensor vector scalar gravity. And the first who really gave this formulation is Bekenstein, for the formulation which correspond to the MOND, to this modified Newtonian dynamics. This is perfectly feasible if you want to describe just the galaxies and the rotational curves. So you could choose to do that. It's a little bit not so easy because you need to, in some sense, have an additional degrees of freedom. These degrees of freedom connected to the vector degrees of freedom, you have in some sense to fit it in order to explain these curves. The problem these theories have is more to the next part of the evidence, which is connected to the growth of structure. So in general relativity, we also are able to explain how the structure form, the fact that you have a growth of fluctuations in GR. When you have a matter dominance. But this does not happen exactly in the same way in these other Bekenstein formulations. So I think, to be fair, is still an open question because there are not so many simulations done with these other theories of gravities because it's much more complicated in that sense to do. But I would say that there is, in some sense, with a particle dark matter, it seems everything simpler, and you don't need, in some cases, also in these modified gravity, if you really want to form structure, you need to add on top of it some dark matter in order to have, as I said, collapse and to have these formation of structure. Because it's not only that we have dark matter there, but also that the dark matter clamps. And this is, in some sense, you need something that clamps. And in this Bekenstein formalism, these additional degrees of freedom usually do not really give you nothing which really have this effect of clamping. I will describe it in a minute. This is exactly one of the evidence from the global analysis.
Thanks.
Yeah, so since also I was asked to talk about particle dark matter, I didn't prepare anything I have to say about these other modifying dynamics. And as I said, this is not always, I would not put it on the same footing. It has not been studied as much as of course, dark matter and general relativity. Okay. More questions? I don't see any hand raised.
Hello.
Yes?
Hello, this is Tanmay.
Yes.
So I want to just clarify one thing. So you write the expression of the dark matter density form that rho over r and with some exponents. So
Yeah.
basically the rotation curve that you are showing, the flat curve, so that is basically the contribution coming from the both dark matter and the luminous matter, right? It is not only the dark matter contribution, because this
Where
is the experiment.
Well, if you are
Yeah,
outside that large radii, the luminous matter contribution is negligible.
yes, that I agree. But if you experimentally measure the rotational velocity with the distance for a galaxy, you measure it from some stars, Doppler shift, or this kind of things. So that anyway cannot say what is this the contribution from the dark matter on the or the luminous matter. So
No,
as a whole, you are measuring the contribution both from the dark matter and the luminous matter. So right. Or,
yes, indeed. So of course, in the gravitational potential, all matter types contribute. Yes, you have the baryons and the dark matter here. But if you reach at a particular radius, you see this is what I was trying to draw here with the disk. This would be what you would estimate for the velocity just taking the density of the disk. So the disk stops at a certain point, or the density goes down quickly, so that you would not have any matter anymore, or at least if you want, the baryonic contribution would start to become negligible.
yes. So my comment is that the solid curve that you are showing, that is basically the contribution from rho dm plus rho luminous, right?
Yes, it's the total if you want, but in the outside part is actually dominated by the halo.
Yes, agreed. And another thing is that that some person was talking about the 3/5 factor. So I think that maybe if you are considering some spherical gas distribution of radius r, so I think that 3/5 factor maybe come from the moment of inertia of a solid sphere. So that I think. So
okay, that may be. I have to chase back my computation. Yes, could be.
okay, thank you.
Yeah. Yeah, but I mean, at the end, of course, the factor is not a key point in the sense that it's a factor for the one. So the important thing is more the dependence on the radii, and this is exactly what I was trying to show you here. Okay, I don't see any other questions, so I would continue with the lecture if everything is okay. Okay, so let me go back now to the issue about the dynamics. So we have this metric, and we have the scale factor. As I said, this expression is quite simple to use for light, and we will get to that later on to connect, for example, to the CMB and the evidence we have from there. But let me go now to of course, the dynamic. So the evolution of the scale factor is determined by the by the Einstein's equation. So if you want to write the whole Einstein equation, of course, it is connected to the Ricci tensor minus 1/2 the g mu nu, the Ricci scalar. And this is equal to 8 pi, the Newton constant, T mu nu for the matter component. Now, I will not go through going through this derivation of this equation, neither I will actually use all these equations and compute the component. Of course, as usual, in principle, you would have to compute from the metric the Christoffel symbol, then the Riemann tensor, and from the Riemann tensor, you can compute the Ricci tensor and the Ricci scalar. So this is a computation, I think, which is standard in GR, and I hope most of you have seen it. So I'm not going to go through it because, especially in doing it on the tablet, it would take me half an hour to go through all. And what I want just to give you here is that from this equation, what you can actually do is to find the two equations which are really important for the case of cosmology, and those are the equations you can obtain from the 0, 0 and I component of this equation, and these are what are called the Friedman equations. So I will just give you the Friedman equation, and as I said, you can find in most books of GR how you get there. And for this equation, I will write for a particular form of T mu nu, which is the T mu nu of a perfect fluid. So I will use T mu nu instead of doing the variation of the Lagrangian with respect to G mu nu. I will use the simpler form where here I have density plus pressure times U mu U nu minus the pressure with G mu nu. And if I use this expression here for the energy momentum tensor, and I obtain two independent equations. One equation is an equation for the Hubble parameter. I will define it in a minute. So here I keep also the curvature just for the time being. And here I have 8 pi gn over 3 rho. And then I have the second equation, which is an equation for the second derivative of the scale factor, which has a minus 4 pi gn over 3 rho plus 3 times p. And here this h square, h is nothing else as the first derivative of a with time divided by a. So this is called also the Hubble parameter. Is it time dependent? Of course, because the scale factor is time dependent. And this is in some sense one of the key quantity which we can also measure in cosmology, and we can see later on how this actually is measured. Now, here you have an equation, as I said, the first one, which in some sense you can also connect to kind of kinetic energy equal to potential energy if you want. So if you look at a spherical symmetric distribution of matter, this in some sense is what would also give you, if you want, also the behavior of a, if you want, of a density under a Newtonian force, if you want, apart from this curvature piece here. And the second equation instead is an equation for the acceleration. And you see that in this case, the acceleration here starts with a minus sign. So for the usual case where the pressure is positive, the density, of course, is also positive. You have here a positive quantity. So the scale factor actually slows down with time. And this is what we have in the usual type of matter like dark matter or radiation. Notice, of course, next week, probably you will see in inflation something different can happen. The pressure there can be negative, and then you can get a different behavior. Now, to solve this equation, of course, it's not enough just to have this equation. We know also we need also to have both. Well, we have one other piece of information actually, which is the conservation of the energy momentum tensor. And the other piece of information we also need, in some sense, to solve the system is to have the relation between pressure and density. So let me get to the continuity equation first. So this is connected to the fact that the energy momentum is conserved covariantly. So if you want this, you can write as a covariant derivative of T mu nu is equal to 0. And if you also go through this equation, which I will go directly to the result, what you find is, you find an equation for the density, rho dot plus 3h rho plus p is equal to 0. So again, you have an equation which gives you the dependence on time of the density. And this 3h is again coming from the, if you want, the Christoffel symbols, from the covariant derivative. And this is exactly connected to the first derivative of the scale factor. And in this case, as I said, the other thing you need is the equation of state. And usually one take a variotropic equation of state, saying that the pressure is just proportional to the density with a proportionality factor W or omega in some case. And this W is just a constant. This doesn't have to be always constant, but for this purpose, we take a constant. And then it's clear that here what you see immediately is that you can rewrite the equation as a rho dot plus 3h 1 plus w rho is equal to 0. And then you remember that h is a dot over a. So what you get here is rho dot over rho plus 1 plus w a dot over a is equal to 0. And from this equation, you see immediately that you have actually a solution for the dependence of the density on the scale factor. And you have this 1 plus w is giving you exactly the power, how the density goes. So if you want, this will also come in one of the exercises. Rho goes like a to the minus 1 plus w. Okay. And this W here is what tells you what type of pressure you have. And of course, you should immediately remember from your electrodynamic course, if you have electromagnetic radiation, then the pressure is just 1/3 of the density. So in that case, W is equal to 1/3. And therefore here you have 1 plus 1/3, which gives you 4/3 multiplied by 3. You have the density going down like a to the minus 4. Instead, if you have the non-relativistic matter has no real velocity, which means the velocity is negligible. This means that there is no pressure. And W then it's equal to 0. And so this is the other famous case. And then if W is equal to 0, then the density goes down like a to the minus 3, which is exactly the dilution connected to the volume. Okay. So in that sense, this is the generic thing. And of course, if you plug in this equation in the previous one, in the Friedman equation here, you can get a solution also for the Hubble parameter and as a function of time. So I'm not going to go through this expression. It's actually one of the exercises you are supposed to do. So I will give you the text of the exercises later. But what is important is to see that you have a different dependence on the expansion of the universe depending on the type of matter present in the universe and also on their equation of state. And this is the key important quantity that we need to know. So if you want, you have, as I said, you have different behaviors, and I can draw a little bit a sketch of what happens. So with here you have, if you want, time or the logarithm of the scale factor. Let me use log of a as a kind of time variable. And here you have, I can draw here instead of the density, actually omega. And omega is what we will use a lot. Omega is nothing else as the density, so omega I in a particular component divided by the critical density. And the critical density is actually 3h squared over 8 pi gn. And this is exactly the density which corresponds to k equal to 0 in this equation. So you see, if this density is exactly Rocklittica, h squared is equal to that, then k here has to be exactly 0. So this is the density which would correspond to this particular case. And indeed, I mean, as I said, we have actually mostly k equal to 0 in our universe. So this in some sense is a kind of reference density. And if you look at what happens to these omega variables for different components, you have different dependencies. And if you write it in this logarithmic scale, they are straight line, but with a different slope. So you have actually three main lines. You have this radiation, you have matter, and here you have, if you want, the cosmological constant. So you see that you have different epoch in the universe, and you have an epoch of equality between matter and radiation, and you have an epoch here, which I call in some case T lambda, where the cosmological constants start to dominate. And you have different behaviors for radiation. As I said, the density goes like 8 to the minus 4. For matter, it goes like 8 to the minus 3. And for the cosmological constant, it's actually constant. So that's why it's called constant. So you see that if you go backward in time, you find different types of matter taking over the evolution of the universe or determining the evolution of the universe. And this has actually quite important consequences. In particular, and this is the last thing I want to discuss today, and then later on I can show you a few plots and a few slides. The important thing is also that you want also not only to describe the evolution of the background, you want also to describe the evolution of perturbation over the background. So we have seen, so I took here the if you want, the Friedman-Robertson-Walker Lemaitre metric in this form, but this in some sense is just the background metric, which is completely homogeneous and isotropic. On top of this metric, you can add fluctuations, which of course are not homogeneous and isotropic, so they have a dependence on space and also on time. And if you want, you can do, so you can do the whole derivation, which I'm not going to do here because it's also quite a long computation, but I just give you the sketch. So we can add cosmological perturbation on the background. So in particular, I have this metric, which was the, I write it as the zero order metric. So this one is exactly the Friedman-Robertson-Walker Lemaitre metric. But then I have a delta G mu nu, which are the fluctuations. And this depends on space and time. And these fluctuations are not homogeneous and isotropic, but they are small. So you have assuming that these, of course, are much smaller than the first term here. And in this case, you can do perturbation theory on the cosmological background and consider what is the equation for the first order perturbation. So go to linear order in the perturbation. This is not always sufficient, of course, but at the beginning, as long as the perturbation are small, the first order is okay. And you can follow then, this of course has the advantage of being linear order. So in that sense, you have equations which are linear in the perturbations, and each perturbation is independent of the other. So that's also the big advantage. So you can classify what type of perturbation you have and consider each of them separately. In particular, you probably will get more about this next week by Chris, but in particular, here you have scalar perturbation, you can have vector perturbation or tensor perturbation. And what I want to see is more the scalar perturbation part, if you want. Yeah, consider just actually, yeah, so I don't want to go through all the derivation because it would again become quite cumbersome. But yeah, so let me see if I can shorten it a little bit. So we have considered the first order equation in the perturbations. And if you want, the two equations I will need is that I can have an equation for the density. So I have a delta, which I define as delta rho over rho zero. So again, also for, this is for the metric, but of course also for the density, I can write rho zero plus delta rho. And also for the pressure, I can write P0 plus delta P. Okay, so I'm doing the perturbation not only for the gravitational degrees of freedom, but also for the degrees of freedom in the energy momentum tensor, if you want. So that to be, and one quantity then I have is this delta, which is delta rho over rho. And at the end, what I end up with is the following equation for delta rho over rho. Of course, I have also to consider the, if you want, self-consistency in the equation, in the sense that, for example, I can consider also gravitational potential, which is determined by the density. And at the end, I have the following equation at first order. So I have a second derivative of delta plus 2h, the first derivative of delta, minus, I have a term which is connected to the pressure, and is actually Cs over a square. So the speed sound, the gradient of delta. So you remember, delta is actually also space dependent. And then I have the part which is connected to the gravitation. So this is the gravitational the Gn, so Newton's constant, and I have a rho zero delta, and this is equal to 0. And this is practically the equation I have for these fluctuations on the homogeneous and isotropic metric. Now this Cs is connected to the derivative of the pressure with respect to the density. So let me write it here. Cs is the speed of sound and is actually nothing else as dp in the rho at constant entropy, actually. So you see that here you have a term which depends also on the gradient of the perturbation. And depending the speed of sound for a fluid, of course, is different. For example, for the case of radiation, you would have here again something like 1/3. But for other cases, you can also have a different expression or a different quantity. And at the end, in this case, then you can look at what happens in this equation. And of course, you have this again. This equation is pretty standard. What happens in an expanding universe? You always have this Hubble term here, which acts as a kind of friction. You have this term, which is connected to the gradient, which, if you want, is yeah. So it acts also like a kind of like in a harmonic oscillator, if you want, you would have, yeah, you would also have in the, for example, in the Klein-Gordon equation, you would have something of this type. Only that here you have a 1/a² because you have the expansion of the universe. And the latter term is actually the term which is giving you the collapse, or if you want, it's actually acting like a force, an attractive force on the fluctuation. And here the sign is negative, as you see. So this means if you would drop these two terms, you see that you have a second derivative And here you have a term also with the delta, with the minus. And assuming that rho 0 is more or less constant, you see immediately that you have a kind of negative mass for the harmonic oscillator. So this means that you have a kind of growth of this perturbation. And this is indeed what is the solution. So actually you can go to the Fourier components. So go to Fourier space. You can write, of course, delta of x as the component in delta k e to the I kx, as usual. And here I am doing this Fourier transform only in the spatial components. And here I can use comoving coordinates. Yeah, so comoving momentum. So in that sense, then in this product, there is no scale factor because each of them is actually moving in the appropriate way. And then what you obtain, the equation is even simpler in the sense that you have, again, the similar expression. And then you have, again, the C square S. Yeah, sorry. No, this is the physical moment. Yeah, this is a comoving momentum, and k square over a square is the physical momentum. And again, the 4 pi gn rho 0 delta is equal to 0. And again, here you see, sorry, here it's a plus. So you see immediately that you have here two competing effects. If this term is large, you have a kind of positive mass for your perturbation. If this term dominates, you have a negative mass. So in that sense, for k sufficiently small, this term will dominate and you have a growth of structure. So you have the fluctuations will grow because of this negative driving term. And on the other hand, if you have here this term, which is large, so for k large, so for the small fluctuations, you would here have no growth. And this is exactly what determines the Jeans length. And this is the separation. So this is exactly CSKJ. It's equal to this square root of this A of t, the square root of 4 pi g and rho 0. And you can see that means that you have actually the length here grows with the scale factor. So you have actually dependence also on time, but generically you can rewrite it also as a function of the Hubble parameter if you want, because here Gn rho 0 you can connect again to the Hubble parameter. So if you really want to do this properly, you can you can rewrite this as a function of Hubble. And rewrite the equation in that form. I'm not going to do it here due to lack of time. But what at the end comes out is that in some sense you have, as long as you are with k smaller than this k, you have actually a growing solution. So a solution which grows. And if you find, you want to find exactly how the solution grows, I can give you the expression. So for k much less than the Jeans length, so when you can neglect the part depending on k, one has it is practically a growing and one decreasing solution. This is typical. You have always also in the harmonic oscillator, you always have plus or minus I omega or plus or minus omega t. And And in this case, the solution, I can give you the expression. It is actually goes like, if you want to keep the K dependence, the decreasing solution goes like the Hubble parameter. And we saw the second derivative of the scale factor is actually negative. So the Hubble parameter usually decreases. Plus you have the second solution, which you can rewrite as in this form. And if you plug in here the expression of the Hubble parameter that you can get from different dominations. So for example, I can take the solution for matter. For matter, we have A of t, and this is also in the exercise, you will have to compute it. You have 3/2, and A of h goes like t to the minus 1/2. Sorry, 1 cubed. Why cannot erase it anymore? Strange. Okay. Yes, so let me check the expression I have. Yes, sorry, this is 2/3. Let me see. Yeah, no, 3/2 is correct. Sorry. Here is 1/3. And then if you plug this in, you see that delta K goes like some other constant. I rescale a little bit so that you have a t to the minus 1, and this is exactly the Hubble here. And then the decreasing solution, and then you have another solution which grows like the time to the 2/3. Now note this time to the 2/3 is also exactly the same as the scale factor. So if you want, the growth of the perturbations is given by the scale factor. And this is an important information to have. Why? Because there we can see how fast the perturbation can grow. And of course, in the if you remember the harmonic oscillator, you would have thought the growth should be exponential. But actually here is not exponential due to the fact that you have this Hubble friction, and you have in some sense also a different evolution, the evolution of the background. And the maximal you can have is a growth which is a power law in the time, and you see it here. And this gives you exactly the growth you actually need to form the structure. Because if I just write it very explicitly, what happens, so the important thing is that the growth goes like A of t in the matter dominance, in matter domination. Now I have not computed it here, but this actually doesn't happen if you have radiation domination, or even less if you have cosmological constant domination. So in that sense, this is also why you need an epoch where matter really dominates the evolution of the universe. And you can compute what happens in that time. So you can have what is delta K of t, depending on the growth, on how the fluctuation was at the time of equality. And the time of equality exactly is the time where the radiation and matter were equal, and the time where the matter started to dominate the energy and density of the universe. And this is actually giving you exactly that this is nothing else as the scale factor at the time t divided the scale factor at the time of equality. And this, if you take here t to be now, for t equal today, this expression of the ratio of the scale factor is not it's just 1 plus z equality, so the redshift of equality. Now redshift is another way for us to keep track of the scale factor. If you remember, I told you that the photons move in conformal time. And this means that since they move with the time which is defined by dt over a of t, they are also, their frequency in some sense is also redshifted accordingly. And this 1 plus z is exactly the redshift that the light has from the time of equality to today. So you see immediately that this factor is important, and the fact that z equality, you can also estimate it from the CMB. It is actually something of the order of 3000. And this is exactly what tells you that the fluctuation from the time of equality to today were able actually to grow by a factor of 1000 or a little bit more. So, and this is exactly what you need in order to start with fluctuation which are very small during the cosmic microwave background evolution. So, for example, in the anisotropy for the CMB, we know that the fluctuation start at the order of 10 to the minus 4. So you so at t equal to CMB decoupling, we have actually delta k over, well, sorry, delta k itself. So depending on the scale, but so let me consider delta in itself and not delta k. Of course, depending on the k, the real size can be a little bit different. But there, the delta is of the order of 10 to the minus 4. And we see that here we have exactly, in some sense, enough time to make it grow to order 1. And it has time to grow to delta of order 1. And of course, as long as delta is small, the analysis I am doing here, it's okay. When you get to delta of order 1, of course, looking only at the linear evolution is not enough. So what you have to do when you start to get non-linear is actually to do really numerical simulation. And that's why actually for really seeing structure formation and seeing the formation of galaxies, clusters of galaxies, etc., we need numerical simulation. Because at a certain point we go beyond the linear order. And indeed, I mean, nowadays, of course, this delta in some places in the universe can be also as large as 10. So we have indeed, yeah, so we have in the nonlinear regime for certain scales. And of course here, as I said, there is a k dependence. So exactly if you are linear or non-linear depend a bit on the scale. But nevertheless, this is exactly what we think happened and how we did form the clusters and the galaxies, etc., through gravitational collapse driven by the growth of the fluctuations. Now, coming back to the question before, if you would have instead modified gravity, then you would have to modify the equation I showed you. And what happens, as I told you already, is that if you try to do this growth of structure in, for example, in this Mond type of setting, usually it's difficult to make the perturbation grow because you do not have, in some sense, as long as you don't have this matter domination. Because here it's important not only that you have gravity, but also that you have, in this equation, in some sense, this equation is valid when you have matter domination. And this equation is actually more generic, but the solution I give you is the solution in the epoch of matter domination. And if you do not have a matter domination, or if matter starts to dominate much later, then of course you are in trouble because you do not have time to really form structures. You would get practically still just a fluctuation of order of 10 to the minus 2 or something like that. And this is not what we see in our present universe. So this is also very strong evidence that the density in matter should be sufficiently large to give you the time to form structure. And this is also one of the very strong hints that the baryons are not enough, because if you would just look at baryons, this time of equality, which I'm defined here, would be much later than the time we have instead considering the dark matter density. Okay, and this one is exactly the discussion for structure formation, which is one of the other pillars in some sense of the evidence of dark matter. It is a little bit more, yeah, so I think it's based on the evolution of the fluctuation instead of the background. But it's also a very strong hint that we need some kind of matter which has especially no pressure, which means it must be non-relativistic. So, and it's also another effect which can show up in these discussions is also the fact if you have a kind of free streaming length like the neutrinos have, and I guess this probably we will also discuss next week when in the lecture about neutrinos. In that case, the behavior, of course, is not the same I am discussing here. Here I am assuming the dark matter is really non-relativistic, so there is no velocity, no substantial velocity. So you don't have, in some sense, the possibility to average out the density, because of course what happens when you have a free streaming length which is non-negligible is that every fluctuation which has a scale which is smaller than this free streaming length would be actually averaged out by the motion of the neutrinos in this case, or any other dark matter with a free streaming length. Okay, so that is more or less all what I wanted to discuss today regarding the evidence of dark matter and a little bit about cosmology. I have actually a few slides which I wanted to show. So let me see if I can do, first let me save this. Okay, I hope I saved it because now I wanted to use the slides. So I have probably to stop it, or I cannot share two things, I guess.
You cannot?
I don't know. I don't see the green. I don't have the green thing anymore. So I guess
in the lower part.
Let me see. Did it disappear here? No, I don't see it. So I don't know where did it go. So I wanted to keep actually the slides to. I hope it's saved. So I did save them. So show in Finder, I saved them in mine. Okay, I see them. Okay. Wonderful. So they are on my computer. Okay, so I have them and I can just go out and probably I can show it again if I need to. Let me see. Yes, so I have to stop sharing here and start sharing the other. Where is it? Okay. I hope you now see a few slides. I don't have so much time. I have probably more slides that I can show, but here is the plan again of the lectures. And here the issue, this is a bit of historical discussion that we had already. I just want to add a little bit this issue about the ballet cluster, because probably this is also one picture you have seen it many times. And this picture is also one evidence that maybe this modification of gravity doesn't really or cannot completely work, because in this picture you can see immediately that the center of mass, if you want, of the dark matter, which is here in blue, does not coincide with the center of mass of the baryonic matter, which is in red. And in this case, the blue curves, or the blue color, is produced through gravitational lensing. Of course, the gravitational lensing gives you information about the total matter, and it is mainly not at the same place as the gas, as you see, which is the red part. So the red curves, or the pink, if you want, is connected to what we see in the X-rays, and this is mostly the gas. And in this case, these two clusters actually hit each other and passed through. And the fact that you have the gas lagging behind is actually connected to the fact that the gas has an interaction. So in that sense, the gas particles cannot really go through each other so quickly as the dark matter, which is collisionless. And you can use this picture, and also the fact that you have this displacing of the center of mass of the two components to put a constraint on the cross-section of interaction of the dark matter. So this one, of course, we didn't discuss yet, but this is one of the evidences we have. Here is the expression. You see it, sigma has to be less than 10 to the 9 picobarns. So if you are a bit familiar with particle physics quantities, picobarns are quite a large cross-section. It's a QCD cross-section or a pion cross-section. So in that sense, the limit is not very strong, but it is strong enough to say that, yeah, in some sense, the dark matter interacts less than the gas in any case. And similar limits you can put also from the sphericity of halos and similar arguments. Because of course, again, if you would have really a strong interaction, then the halo would be more spherical than they are. And here again, there is a picture, a real picture of the rotational curves, as you can clearly see. There again, you have also the different components that you can look at. Yeah, so you have the halo component and the disk component and the gas component. And again, the argument is exactly the same as what we went through during on the slides. And here is again the famous point: what happens in the center. And as I said, here you have different possibilities. You could have a core, you could have a cusp, and probably if you work in dark matter, you have heard a lot of discussion of this issue. And we will come back to this in today's time. And of course, the other big issue is also the velocity of the dark matter in our galaxy. And this is another thing we don't know very well. There will be also an exercise probably tomorrow about this, but generically one thinks, or often it is approximated with a Maxwell-Boltzmann distribution, but it's not really like that. It's not clear. It's here, for example, is the expression coming from a fit of some years ago of the data, dynamical data of the galaxy. And you see that you have a kind of a band, so it's not exactly a Maxwell-Boltzmann. And also other numerical simulation nowadays tell us that the distribution of velocity is probably not exactly Maxwell-Boltzmann. And here is the evidence I was talking about from the data. In particular, one of the best measurement we have on the density of dark matter is connected to the cosmic microwave background. And here you see the peaks in the cosmic microwave background. And in particular, the position and the height of the peaks can constrain the cosmological parameters. The difference between even and odd peaks gives us the baryon density pretty precisely. And as I said, the position of the first peak tells us that we are more or less in a flat universe. But the other also position and height of peaks give us also the density of dark matter. And I have a better picture later on. So let me go here shortly through this discussion about the fluctuation. Here again, it's the issue of following the fluctuation from the CMB time to today. And okay, assuming that inflation sets the initial conditions, this is the equation, is exactly the equation I showed you. And again, you have that the growing solution is exactly the one I showed you also. And in that sense, you can see this growth of fluctuation also from numerical simulation. And here are some pictures of some simulation by Volker Springer some years ago. You see that you have a kind of more homogeneous type of universe at the beginning at Z here of the order of 18. And then if you go towards Z equal to 0, you have that the densities, the density contrast grows. And indeed, in this epoch, you are already practically non-linear on this length scale. You see here, this length scale is about megaparsecs, 100 megaparsecs is indicated on the picture. And here is a little bit the summary of the different scales. So as I already told you, how large a fluctuation is depends also a little bit on the scale. Because of the time the fluctuation had to grow. So some scales and the fluctuation grow only after they are smaller than the horizon, which is set by the Hubble scale. So in that sense, you see here the CMB scales, which are coming within the horizon practically now, they are still relatively small. So you see here in red, you have values about 10 to the minus 4, 10 to the minus 3 for those fluctuations. But instead, if you go to fluctuations which are on smaller scales, which enter the horizon earlier, they have had time to grow. And indeed, if you go even to smaller scales, you get to something larger with density fluctuation larger than 1, which is exactly in the nonlinear part. And okay, here I had also a few slides on which are practically connected to what we had also discussed in the lecture. But I want just to show, of course, the issue about isotropy and endomogenity. Here you have a picture, of course, of the cosmic microwave background spectrum, and you see that it's actually the same spectrum in all directions, which is really telling you that these isotropies are really very good approximation. And it's also the fluctuations are, of course, very, very small. And here, of course, you see also from the structure formation, here it's a little bit older picture, but I kept it because it's a bit easier to see. But you see, if you go to further distances, the density becomes lower, and also it becomes a bit more homogeneous in that sense. And the idea is that the further you go, the more in the limit of homogeneity, the better it is. This one was also, let me try to this is probably too much. Yes, I am at the end of the lecture. I wanted to show you probably just one last thing, which, yes, so which was again on the CMB. Of course, nowadays we have also the data from 2018 from Planck. And from this data, we also have a pretty good picture of what is the density of matter. And here you have the plot of the density of matter with respect to the Hubble parameter. Of course, as you all know, the Hubble parameter is a little bit discrepant to what we measure from CMB and what we measure from the supernovae, for example, and other measurement. But nevertheless, these, of course, has a little bit of influence in the sense there is a kind of degeneracy with the dark matter density. Nevertheless, we have a quite good determination of the density of matter from the CMB, as you see here. And doing the global fit gives us with a better precision than 10%. So this is exactly what tell us what kind of density the dark matter has to be. And this is what we will try to match, of course, tomorrow. Okay, so that's all for today.